I get 8 points. So it's like this. Interest. And then we got like chill. But look at best to be plans.
Yeah.
I got French.
French.
I just do the math homework. It's more than
Okay, we're going to continue with our notes from yesterday. So in your packets, let's go to page 3. Okay, so today, again, this whole week is all review. You've all seen this before, but I think it's good for us to just to recap and to review and to have this, yeah, to be able to know that these are going to be topics that we're going to be using over the course of the semester. So rational functions. So rational functions are going to be functions where there are variables in the denominator and potentially in the numerator as well. Let me highlight a few of the properties that we're going to, or properties we're going to find with these graphs. So first thing is finding vertical asymptotes. So the way we find vertical asymptotes, we're going to look at the denominator, finding factors in the denominator of our rational expression. Okay, we're going to set the expression in the denominator equal to 0 and solve for x. And then we want to make sure that the factors do not cancel with the numerator. If a factor in the denominator matches with the numerator, then that's going to be location for a hole. So the way we find a hole in the graph is if we see identical factors in the numerator and denominator, we can pair them up, we can cancel them out, and that will tell us a location that there's a hole in the graph. And I'll walk through how we can find that particular order pair where that hole lives on the graph. Next, finding horizontal asymptotes. So this is going to be the way we find it algebraically or looking at an expression is we compare degrees between numerator and denominator. So we look to see what's the highest degree in the numerator versus the highest degree in the denominator. And if the degrees are the same, then we do have a horizontal asymptote, and it's just the ratio of the coefficients. We should look at the numbers attached in front of those leading variables, and then we just write that the ratio of those numbers will be the location of your horizontal asymptote. If your denominator has a higher degree than your numerator, it could be x squared over x cubed or x to the second over x to the fifth. As long as your denominator is a higher degree, it will always be a horizontal asymptote, but it's always going to be at y equals 0. And if your numerator is greater than your denominator, there is no horizontal asymptote. Now, there is a chance that this scenario could lead to a slant asymptote, but in this course, we're not going to see much of that. So we don't have to worry about slant asymptotes. Okay, so number 9, x plus 2 over 3 minus x, or y equals x plus 2 over 3 minus x. Are there any holes in this graph? No, right? There's no common factors that can pair up and match up. We can't just pick out the x's and cancel these out. So there are no holes. Is there a vertical asymptote? Okay, and where do we look? Okay, where do we look for vertical asymptotes? Numerator or denominator? Denominator, yep. So we do have a factor that we can look for that. So we set 3 minus x equal to 0. We solve for x equals 3. So there's our vertical asymptote at x equals 3. We said there are no holes in the graph, so we'll say none. Vertical asymptote, x equals 3. We want to make sure that we don't just say 3 for vertical asymptote. We want to be able to name the equation of that line. So a vertical line is always going to be, that equation is always going to be x equals. A horizontal line is always y equals a number. All right. Do we have a horizontal asymptote? Degrees are the same, so it's going to be option A. We'll just take the ratio of the coefficients. The number in front of x is 1. The number in front of negative x is a negative 1. So negative 1 over negative 1 is negative 1. So my horizontal asymptote will be at y equals -1. Two more properties that I think are useful for us to know. I'm going to write that up here. I did not put that in the original set of notes. Is finding x and y intercepts. The way you find x intercepts is we set the numerator equal to 0, at least the numerator that don't cancel out. If numerators cancel out, then we know that's a whole, but any numerator expression that does not cancel out, that's going to be where we can find our x-intercept. X-intercept is the part of the graph that crosses the x-axis, right? So we set the numerator equal to 0 to find x-intercept. To find y-intercept, we're going to replace every x with 0 and then solve for y. So after all the x's 0 out, we look to see what's left over. Okay, so we do have an x-intercept here. We can set the numerator equal to 0, x plus 2 equal to 0. X equals -2. So my x-intercept is going to be at -2, 0, right? Any order pair that lives on the x-axis will always have a y value of 0. And then y-intercept, replace every x with 0 and see what's left over. 0 plus 2 is 2. 3 minus 0 is 3. 2 over 3 is 2/3. So y-intercept is 0 2/3. And then every order pair that lives on the y-axis will always have an x value of 0, right? 0 2/3. Okay, let's add that to our list of items. So -2, 0. I didn't have a place for y-intercept, so we'll just put that to the side. Y-intercept is at 0 2/3. Now, the nice thing about all these properties is we can produce a relatively accurate graph without having to look at every single order pair, without having to look at the graphing calculator. And the asymptotes really help us with that. The asymptotes allows us to know how our graph is going to, we know that our graph is going to move towards the asymptotes as we move away from the center. So having those properties really help and allows us to get a quick sketch of the graph without having to look at every single detail. So let's see if we can get a decent picture of the graph just based off of these properties. Right, vertical asymptote at x equals 3. Let's go ahead and graph that. Horizontal asymptote at y equals -1. The x and y intercept will really kind of help us give us some anchor points along on our graph. So -2 0, 0 2/3, under 1. So I'll put that here. Now we know these 2 points will connect, and the fact that the graph is rising from left to right, it kind of gives an idea how our graph's going to look without even having to look at any other order pair. We know our graph is going to have to kind of hug along the asymptotes as we get further and further away from the center. So we kind of have an idea how our graph is going to look. And the asymptotes really help us with that. Now we know that there's also a graph that's going to live to the right of the vertical asymptote. The only question is where it's going to live. Is it going to live in this little, is it going to be kind of hugging along the axis above, or it's going to be below? And we can just test an order pair. So I'm just going to pick a point to the right of 3. Maybe I'll choose 4. And I just want to know, am I going to get a positive number or a negative number? Negative number will probably be down here. Positive number will most likely be up here. So if I plug in, let's say 4 or 5, let's say I plug in 4. 4 plus 2 is 6. 3 minus 4 is -1. 6 over -1 is negative. 6. So that's going to be somewhere down here. We don't even have to worry about what that order pair is. As long as we know our graph is down here, that's enough for us to sketch a graph that follows along the asymptote. Okay, so with very minimal information from order pairs, we can still get a pretty good sketch of the graph as long as we have some anchor points and some asymptotes to kind of help us along the way. All right, number 10. We always want to try to factor first. Do we see any ways of factoring in this? Yep. Yep, denominator. We can do difference of, yep, difference of squares, x plus 3, x minus 3. What about the numerator? Yeah, take 4 out. I'm left with x minus 1. Okay, good. Having my numerator and denominator in factored form, it allows us to see all the different components a little better. Do we have any holes here? No, no holes. Okay, so we have 2 vertical asymptotes. The numerator, we can find x-intercept. If you want to find the horizontal asymptote and you're trying to compare degrees, look at your original expression. It's a little bit easier to identify your degrees relationship. Sometimes the factor form, it doesn't quite get us. It doesn't hide some of that information. So I like to find x-intercepts, holes, and vertical asymptote at the factored form. But to find the horizontal asymptote, I think it's easier to see the relationship at the original stage than the factored form. So here, if we look at the numerator denominator has a higher degree, which means that there is a horizontal asymptote, but it's always going to be at y equals 0. Okay, let's see how much of this we can find as we work at the same time. So x-intercept, set the numerator equal to 0, solve for x, I get 1. To find the y-intercept, replace all the x's with 0 and see what's left over. I get 4 over 9, positive 4 over 9, which is close to 1/2. Okay, let's see if we can do a rough sketch of the graph just based off of these properties here. Okay, vertical asymptote at 3 and -3, x equals 3, x equals -3. Horizontal asymptote, y equals 0. X-intercept, 1, 0. Y-intercept, around 1/2. So I'm going to just plot a point. The fact that my graph is decreasing, that's kind of indicating that my graph is going to kind of have this negative slope in this middle region, and eventually is going to kind of gravitate towards the asymptotes. I do want to point out something about vertical asymptotes versus horizontal asymptote. I think we all kind of have an idea that our graph can never cross the vertical asymptote, right? It really separates different parts of the graph for us. But what seems kind of strange is, how is this graph able to cross through the horizontal asymptote? I thought, we would think that, oh, maybe there should be a restriction here, right? We shouldn't be able to allow this. Now, there's horizontal asymptote is a little bit different than vertical asymptote. Horizontal asymptote is describing the end behavior of how the graph is going to be. So the dotted line is really for the edges. It's really indicating how the graph is going to look like as it exits the graph. So it's more of a description of the end behavior. It's not a restriction for how the graph is going to cross. So the dotted line here is not preventing the graph from crossing over. We can really ignore the dotted line here. Really, dotted line is only for the edges of the graph in terms of how the graph is behaving. So, it seems strange that the graph can cross over the horizontal asymptote, but really, the dotted line is really for the edges and not for the middle of the graph. Okay, we have 3 separate regions, right? Region to the left of the first asymptote, and then middle, and then to the right. So I'm going to just pick point to the right because I know that if I can find an order pair either above or below, that's enough for me to figure out how my branch is going to look. So if I choose, let's say 4, I'll get 12 minus, if I chose 4, 16 minus 4 is 12, and then 4 squared minus 9 is a positive number. So positive over a positive, that's enough for me to know that my graph is going to live up here. And then having the asymptotes there kind of helps me shape my graph. I know that there's another piece of the graph that's over here. So I'll choose -4. If I choose -4, I'll get a negative up in the numerator, and I'll get a positive in the denominator. Negative over a positive is negative. That's enough for me to know my order pair is going to live down here. And I don't really have to worry about plotting any points. I can just use the asymptotes to kind of give a quick sketch of the graph. So with minimal information from order pairs and just knowing how the asymptotes will affect the graph, we can get a pretty accurate picture of the graph without having to painstakingly look for every single order pair or to have to look at the calculator. All right, let's see if we can work through 11 and 12. Can we factor parts of the numerator and denominator here? Okay, numerator, there's a factor of what? GCF of x. Denominator, I'm going to take an x out, and then we can look at trinomial factoring. Multiplies to be 6, adds it to be -5. Okay, look at the factor form for 11. What do you see here that we haven't seen before with the previous 2 problems? Yeah, we have holes. Okay, so there's how many holes do we see? 2, right? We have 2 factors that cancel out. So we know that there are going to be 2 holes in the graph. So there's going to be a hole at x equals 2.
So what if you have, is it like x-intercepts take priority if you have like 2 holes?
Yeah, it's a good question. So if any factors cancel out, we know that they can never be an x-intercept. Now, if there's another x in the numerator, or x factor in the numerator, then that will be where an x-intercept would live. But here, there are no more x's left up top. So do you think we're going to have an x-intercept? There's no x-intercept here. Yeah, so if there's any leftover x's up in the numerator, it'll be an x-intercept. If there's a leftover factor in the denominator, it'll be a vertical asymptote. Okay, good.
What if there's 2 holes at the same? Like, what if there's like, you have like x minus 2,
Mm-hmm.
and like those cancel out, and you have another x minus 2?
Oh, I see.
Another hole.
I think in that case, like an x minus 2 over x minus 2 squared, like that.
Yeah, something like that.
So this is where there's a hole at 2 and there's a vertical asymptote at 2.
Yeah.
What that look like? Yeah, so I think in this case, the vertical asymptote kind of, yeah, we don't really see a hole here. The asymptote really kind of take precedence over the hole. Either way, the graph doesn't exist at 2, but we don't really see a hole because everything is being canceled out with, yeah, it's kind of a strange case.
Yeah, all right.
Yeah. Okay, we have 2 holes, right? 0 at 0 and at 2. So the way that we find y values of holes, we want to get this down to a reduced expression. So the reduced expression is removing all the holes, and then we're left with 1 over x minus 3. This is the version of the graph if the hole was not there. So the way you find the y values of the holes is you find the common factors that cancel out between numerator and denominator, and then you plug these x values into the reduced version. Because if you don't plug into the reduced version, if you plug into the original version, you're going to get 0 over 0. You're not going to get the location of the hole. So by plugging into the reduced version, we're able to get a number, and that number will correspond with the y value where the hole lives. So if I plug 2 in for x, 2 minus 3 is -1, so 1 over -1 is -1. If I plug 0 in, 1 over 0 minus 3, that's -1/3. So we have 2 holes. Now, the holes I think, are useful because we can treat them like ordered pairs in the sense that you know your graph is going to have to kind of connect through those holes. So these holes will kind of help us figure out where the graph is going to be. All right, we do have a vertical asymptote here, right? Where's the vertical asymptote? X equals 3. Horizontal asymptote, we can go back to our original equation, compare degrees. You can see that the denominator has a higher degree than the numerator. So if that's the case, your asymptote will always be at y equals 0. Zoom in. X-intercept. We see that after all the holes have been removed, there's not going to be any leftover x in the numerator, so we don't have an x-intercept. And to find the y-intercept, we want to replace every x in the original function with 0. We're going to get 0 over 0. That's undefined. We don't have any y-intercept. Okay, let's see if we can get a picture of the graph. All right, vertical asymptote at x equals 3. Horizontal asymptote at y equals 0. Holes at 2, -1, and 0, -1/3. Even though these are holes, we're going to treat them like ordered pairs, which is put an open circle where these are. But we know our graph is going to have to move towards these holes. So the fact that I have a hole that is higher up than the other hole, and I know that I can see that if I were to connect these two, my slope is going to be decreasing, and that's going to allow us to kind of see, okay, that along with the asymptotes, we can kind of get a pretty good feel for how our graph is going to look. Sorry, I meant for this to be an open circle there. Okay, and then we know that there has to be something to the right of the vertical asymptote, so I can test 4. I can plug 4 in here, but maybe it's easier to just plug 4 into the reduced expression. All I care about is it going to be up here or down here? As long as I know where it is, I can use the asymptotes to kind of help give me a picture of the graph. So if I plug in 4 or 5, I'll get a positive number, 1 over 2 or 1 over 1. That's enough for me to know my graph's going to live up here. All right, can we try 12? Factor as much as you can. And just like how we did 9 through 11, identify any potential holes. look for potential x-intercepts, look for vertical asymptotes. Some of them may not exist, so let's see if we're able to identify which ones have values and which ones have none. But start by factoring first. Factor as much as you can before you look for vertical asymptotes or holes. Give you guys a minute to start, and then I'll walk through the steps with you. And we really can't factor the numerator x squared, 5x squared plus 2. I mean, we could factor using imaginary numbers, but in this course, we're not going to be dealing with, we're just going to be dealing with real number systems. So nothing we can do with the numerator, but denominator, we can take out a GCF of 3 and then continue with difference of squares. Horizontal asymptote, you go back to your original equation. The degrees matches, so we just pick off the fractional value between those two numbers. X-intercept. We would try to find the x-intercept by setting the numerator equal to 0. But if we try to solve for x, you'll get 5x squared equals -2. Take the square root of a negative number that doesn't exist, so we don't have any, none. Y-intercept, go back to your original equation, replace every x with 0, see what's left over. I'm left with 2 over -12, which is -1/6. Okay, let's see if we can get a picture of the graph just from these few properties that we have in front of us. Five thirds is a slightly less than 3. Sorry, less than 2. 6/3 is 2. 5/3 is slightly less than 2. I do have a y-intercept that's 0, -1/6. Gonna plot a point here. So let's say I want to plug in I want to have an idea how the graph is going to move to, what's going to look like in this middle region. If I plugged in 1, I'll get 7 over -9. If I plug in -1, I'll get the same thing, 7 over -9. So that tells me that both points are below and they're going to be kind of symmetrical. So it's going to be kind of a parabola shaped in that middle region. All right, to the right, if I plugged in 3, I'll get 5 times 9, 3 squared. That's 45 plus 2. That's going to be a large positive number. And then 3 times 3 squared minus 12. That's also positive. So 2 positive. I'm going to, it's going to be in this positive region up here. Same thing. If I plug in -3, all the negatives will cancel out with x squared. So I'm going to get a same y value. So my graph will be up here as well. Okay, page 4. Let me just do one of these examples, and then I think the rest you guys can probably try later with homework. So number 14, it says find the domain and range expressed in interval notation. Find all horizontal and vertical asymptotes. So domain is how far the graph stretches from left to right. So we want to start as far left as we can go. And the arrow here is indicating that it extends all the way to -infinity. So our domain, let's go from -infinity until where we see our first vertical asymptote, which is at -1. And then you can do comma or union. And then we pick up to the right of the vertical asymptote. So between -1 and 1. And then to the right of the vertical asymptote. So from 1 to infinity. Okay, range. Range is where does the graph exist in terms of the y values? So range, we want to start as low as we can. So we start at the lowest y value. We see the arrows are going down to infinity. So -infinity 2. And it goes all the way up to what? To 3, or 2, sorry, 2, right? And then it goes all the way up to 2. Bracket or parentheses? Bracket, because it actually does hit that point, right? So it's not an asymptote there. So we do want to indicate that the graph does touch that point. Now there's a break from 2 to 3. There's nothing that lives between 2 and 3. So we're going to jump to above the asymptote. So we're going to pick up again from 3 to infinity. What are the notations around that? Parentheses, because the asymptote around that 3 is indicating that the graph is never going to touch 3. It's always going to live slightly above 3. So parentheses will ensure that we never go all the way down to 3. We start slightly above 3 and we go to positive infinity. Okay, we can tell where the horizontal asymptote is. We can also tell where the vertical asymptotes are. Okay, I'll leave the rest for you guys to do later. Let me just see if I can go through parent graphs with you. So page 5 and 6. Okay, so today I want to go over parent graphs, and tomorrow we'll take those parent graphs and we'll do transformations. The nice thing about parent graphs is that if we know what a parent graph looks like, then even with transformations, we can have a kind of a ballpark idea of how the graph is going to look and where the graph is going to be without feeling like we're completely lost and we got to use the calculator to know how the graph is going to look. So, being able to have these big pictures allows us to have a sense of how our graph is going to look without having to look at all the details of order pairs. So the parent graph for linear function is y equals x. This is a graph with a positive slope that's kind of rising at a 45-degree angle here. So linear graphs, exactly what the name suggests, it's going to be a line. Typically, it's as long as the graph is not a horizontal line, your graph is always going to be either rising or falling. In this case, for my parent graph, my domain, your domain for linear graphs will always be all real numbers. And as long as there's a slant to the graph, your range is also all real numbers. End behavior, as long as my graph has a positive or a negative slope, the arrows will always be pointing in opposite direction. One will be going up and the other will be going down. So as we follow the left arrow is going down to negative infinity. As we follow the right arrow is going up to positive infinity. So your linear graphs can look different depending on where the y-intercept is and depending on what the slope is, but they're all going to have these very similar behaviors. Quadratic functions, these are graphs where your highest degree is x squared. So it could be 4x squared, it could be x minus 2 quantity squared, it could be shifted all the way around, but the arrows will always be a curve, and there will always be a vertex. There will always be either a highest point or lowest point, and the arrows will always be pointing in the same direction. So in this case, y equals x squared, my graph is going to be both pointing up. Okay? Domain, all real numbers, and the range is going to, your range will always have one infinity or negative infinity on one side, and the other side is always going to be the highest point or lowest point of your graph. Cubic functions, y equals x cubed. Sorry, y equals x cubed. Your cubic functions will always, the arrows will always point in different directions. And that goes to just some general properties that we can identify. Whenever I have an even degree, my arrows will always point in the same direction. If I have an odd degree, then my arrows will always be pointing in different directions. Reciprocal, these are rational functions. This is where you have an x in the denominator and potentially an x in the numerator. The parent function is going to be 1 over x. And typically with rational functions, you're going to have at least one vertical asymptote and also one horizontal asymptote. Not all, but the ones that we work with are going to have a vertical and a horizontal asymptote. Here, if I said the denominator equal to 0, I'll get x equals 0. So that's why there's a vertical asymptote at x equals 0. Here, my numerator degree is 0. My denominator degree is 1. Denominator has higher degree. So the horizontal slope is at y equals 0. There are always going to be branches that, and all the branches are going to be impacted one way or another by the asymptotes. Okay, let's see if we can finish page 6, going over the major paragraphs. Next up, we have y equals square root of x. Y equals square root of x, radical function. Think of this as half of a sideways parabola. Basically what it is. Half of a sideways parabola. Radical function is basically the inverse of an x squared. If we were to fold that graph over y equals x, the diagonal line is going to end up looking like half of a parabola opening up. So all your radical functions will have a starting point, and it'll move. In this case, this is moving to the right, but it could move to the left if it's a negative or a square root of negative x. Cube root functions. Think of cube root functions as the inverse of a cubic function. So if I were to take a cubic function, and if I were to fold the graph over the diagonal line y equals x, it's going to end up looking like a cubic function. Sorry, cube root function. We're not going to see too much of cube root functions, but it's just good to see some connections between a function and its inverse. What we will see a lot of will be exponential function e to the x and log function, natural log of x. So exponential function, it doesn't have to be e to the x. It could be 2 to the x, 3 to the x, 4 to the x. But the one that we're going to see the most often is going to be e to the x. But all exponential functions has the form that there's a base that is a constant, and then a variable that lives in the there's an x variable that lives in the x form. And all your exponential functions will have the behavior of it'll be flat on one side, and all of a sudden the graph will increase in steepness very, very rapidly. A natural log function is the inverse of exponential function. So I drew this dotted line here to show that if I were to fold this graph over this dotted line, it's going to end up looking like a log function. So exponential and log functions are inverses of each other, meaning that if I were to take every ordered pair in my exponential function, and if I were to flip-flop it, every x becomes y, every y becomes x. This is the graph I'm going to see. And because the x and y's are flip-flop between exponential and log functions, we're going to see all these other properties also have a flip-flop relationship. So if you look, the domain of one is the range of the other. The range of one is the domain of the other. There's a horizontal asymptote for exponential function, but no vertical asymptote. There's a vertical asymptote for a log function, but no horizontal asymptote. So everything that is true for x becomes the property for the y. Everything that is true for y becomes the x. So it makes sense that everything is flip-flop. Ordered pairs are flip-flop. Properties are flip-flop. Asymptotes are flip-flop. So if we know the shapes of these graphs, then we should be able to look at a transform graph and at least have some idea where the graph is going to live, as well as how the graph's going to look. Okay, one more absolute function, y equals absolute value of x. So absolute value function always has this V shape to it. It could be a V right side up or a V upside down. But sometimes it's hard to work with an absolute value function. So sometimes we like to think of an absolute value function as two linear graphs that just happen to have a starting and ending point. So we can think of absolute value of x as a graph of y equals x with a positive slope that happens to start at 0 and only showing to the right of 0. And then y equals negative x, that's only showing to the left of 0. So we make the two graphs show only a certain part so that the v shows up and not an x. So sometimes we'll be rewriting an absolute value function as a piecewise function to make it a little bit easier to interpret. Okay, so tomorrow we're going to do transformations of these parent graphs. Then we'll look at trig, and then Thursday we'll look at logs and exponentials, and then Friday we'll try to put it all together, do an overall review. Again, no assessments for this unit, but I will be checking your packet on Monday, next Monday, for homework grade. All right, come get your phones. Great.
Yes, it's in your bag.
What's with this? Because I noticed you have a classroom.
Yeah, the bathroom is just across the hall, so you can just go.
Okay.